This video is going to be an introduction to vertical circles. We've been talking about horizontal circles so far, so let's jump into vertical circles. Let's see, hello horsey and cow and car, we'll kind of zoom those away. The first example I want to talk to you about is a swing. So let's draw somebody on a swing at some various locations, just from a side view. Good, so here's the person on a swing, and there we go, and they're up here now. And what we're going to do is let's use tension as our force, even though when you're on a swing, you're technically sitting on a seat, and I guess that would be a normal force, but let's just talk about the tension right here. So in particular, I'm curious about the bottom of the swing right here. Obviously, you're swinging back and forth, and I want to take a situation where you're at the bottom of the swing right there. You can see that you're going in a circle, a part of a circle. And let's draw a free body diagram for what's going on right down here at the bottom of the swing. So if we're looking from the side view right here, we've really just got two forces that are going on. We've got gravity going down, and like I said, we're just going to concentrate on tension over here. And this is going to be a tension going up. What I know is that I actually need to have a higher tension force than gravity, because if I'm going in a circle, I need to have a force towards the center of a circle. Remember, you need, just write it up here, you need a centripetal force, meaning a force pointed towards the center of the circle. For these vertical circles, we're always going to be having a balance between gravity and tension. So when we say we need a centripetal force, the centripetal force is actually going to be the net result of a couple of different forces. So I have that written out over here. I say when you're on a swing, the net result of gravity and the tension creates a centripetal force. So it's not just one force right here we're worrying about, it's actually two different forces. And if I look at this situation over here, I can write that we have a net force. Remember, that's the overall result of everything, and that is going to be tension minus gravity. That is going to create, the net result of that is going to create a centripetal force. That's my FC right there, centripetal force, right? So this one has to be bigger than this one in order to have an overall result of pointing you towards the center of a circle. Now you can imagine what would happen if you were riding a swing and you're coming down this way and all of a sudden the chain broke on the swing, right? Well, what would be your path? You would continue to go in a straight line. You wouldn't go in the circle again. You wouldn't swing up in the circle. You'd go in a straight line and then eventually fall down because all you'd have is gravity acting on you. So you need the tension to be bigger than gravity once again to have a net result pointed towards the center of a circle. So let's play around with some numbers here. Actually, one thing that I wanted to point out is, let's play around with some numbers here. And let's see what we can do. So let's just make some estimates here. Let's say that we're on a swing and we'll have a radius of 5 meters for a swing. This is a pretty small swing set. So that's a distance from there to there. We'll just call that to the middle of your body. And then let's say that at this bottom spot right here, let's say you're going pretty fast at 10 meters per second. That's like 20 miles an hour. And then we're going to actually need to work with mass in these problems. So we'll just give the person a mass of 50 kilograms just to keep the numbers really easy. And what I'm really curious about here is, what is the tension? What is Ft at the bottom of the swing? What's the force of tension at the bottom of the swing when you're swinging along? Okay, so that's just a nice calculation to be able to do. What's the force of tension at the bottom? So how do we figure that out? Well, we're going to work with this equation right here to figure it out. Let me give you all just a quick reminder that when we're dealing with centripetal force, the formula that we're using, centripetal force is m times v squared over r. The v squared over r part is our acceleration. Force is mass times acceleration. Okay, so let's put this all together. We're going to write it down here. We're going to have tension, gravity, and centripetal force. So there's tension, just writing the same thing again. Minus gravity equals centripetal force. But if I'm curious what the tension is at the bottom, I'm going to write it like this. Force of tension equals the centripetal force plus the force of gravity. So I just pulled that to the other side. algebra. And now this I'm going to stick in over there so that I can write some numbers down here. Oh, also reminding you that the force of gravity, just write it up here, is always m times g. That's how much something weighs. So let's put those things together. So force of tension is this one right here, m times v squared over r plus m times g. Now we can actually come up with a number for this because that's a number that I know. That's a number, right? These are all given over here. So let's just plug in numbers and we'll figure out what the answer is. So I'm going to drop my units because it's going to get kind of messy in here. So 50 is my mass. Velocity is 10. Don't forget to square it. Radius is 5. M is 50 again. Oops, that shouldn't be equals, that should be plus. And then gravity's 10 again. Really should be 9.8, but that's close enough. And if you add these things up and you do it all, then you'll get that the force of tension is 1,500 newtons. Okay, so what does that mean in relation to, I don't know, anything else? Let's figure out what that 1,500 newtons means. And what we're going to do is let's relate it to, what about if this person were just hanging from a rope without swinging? What would the force of tension be in that situation? Well, if you're just hanging there and you're not swinging, then in that situation, the tension and the gravity are going to be equal to each other, right? Because you don't need any extra force putting you to the center of the circle. So if just hanging there, then the tension is just the force of gravity, and that one, for something that has a mass of 50 kilograms, is going to be 500 newtons. So when you're on the swing, the tension is actually 3 times as much as when you're just hanging there. What that's going to feel like in your body is it's going to feel like you're pulling basically 3 Gs. It's going to be 3 times your body weight. If you're just hanging there normally, then that's 1 G. You're going to sort of feel like you're being pulled down with 1 G just from normal gravity. And this is adding on an additional 2 Gs on top of it. So it's like feeling like 3 Gs. So that would be a pretty extreme swing ride. And you all will get a chance to go on the swing and figure that out. So let's do one other example here, as I want to do like a roller coaster example, because roller coasters go in loops. So let's do a roller coaster. All right. And then we're going to draw a side view of a roller coaster, just a simple loop roller coaster like this. We're going to go through a loop just like that. Great. I have another diagram here, and everything's going the other way. So I'm actually going to make us go this way through the loop. So you're in a roller coaster. Okay, there's multiple cars on the roller coaster. And I want to talk about what it feels like to go through the loop upside down like that and then come all the way back out. So let's talk about what's happening when you're upside down on a roller coaster like this. Okay, so there you are, and if you're sitting in here, there's your head, there's your body, like you're upside down in the roller coaster. Good? So what's happening here when you're upside down? Of course, if the roller coaster were just parked there and it weren't moving, you'd feel like you're being pulled down by gravity, and that wouldn't be very comfortable. It'd be really, really scary. So what roller coaster designers want is they want you to feel this centrifugal force pulling you into your seat. So you want to feel a centrifugal force pulling into your seat. That's going to make you feel like you're stuck there and that you're not about to fall out. Because if you're upside down and you feel like you're going to fall out, that's going to be pretty scary. And I know you've got a strap on, like a shoulder strap or something, but you don't want to feel like every time you go upside down, you're about to fall out of the roller coaster. So you need to feel this centrifugal force. The centrifugal force that you're going to feel is going to be equivalent to what the normal force is on your body. So whatever the normal force is on your body, that's sort of what you're going to feel like is the centrifugal force. Why is that the case? Well, let's think about if you're just standing flat on the ground. When you're standing flat on the ground, gravity is actually pulling you down, right? And you've got a normal force pushing you up. This normal force that's pushing you up is kind of giving you the sense of this gravity pulling you down. You actually don't have any sensors on your body to tell you that you're being pulled down by gravity. All you can feel is that the floor is pushing you up. And when the floor is pushing you up, your body interprets that as you actually being pulled down. Remember, there's this sort of opposite effect, right? Like if you're in a car, oh goodness. going to draw the car here. Okay, good. So there's your car. Oh, that was a pretty bad car. Anyway, here's the car. So when you're in the car and the car is accelerating forward, you feel like you're being pulled back. Same thing. When the car is slowing down to stop, you feel like you're being pulled forward. So it's kind of always this opposite thing. In this situation up here, when you're in the roller coaster, you need this centripetal force. So there is a centripetal force putting you towards the center of the circle, and you feel like you're being pulled to the outside of the circle. And that's a comfortable feeling when you're upside down, to be pulled towards the top. And if we draw a free body diagram for this situation up here, it's going to be pretty interesting. So let's draw the free body diagram. So there's you. Of course, we've got gravity pulling down. And there's another force, which is the normal force. So I'm going to draw this here. Now, free body diagrams can get a little messy sometimes. Now, I actually don't know right away which one of these is going to be bigger. It's going to depend on the situation and how fast you're going and what the radius of this, the radius of the loop is going to be. So right now, I've just kind of drawn them about the same length each, but one of them could be bigger, one of them could be smaller. It just kind of depends on the situation. But what's going to happen is you're going to feel whatever the value of this thing is right here is what you're going to feel like is pulling you to the outside. So you really want there to be a normal force on you because that's going to be pushing on you when you're upside down, and that pushing on you when you're upside down is actually going to make you feel like you're being pulled up. So in this situation, it's a little bit different than what we had before, and what we have on a roller coaster is the net result of gravity and the normal force is going to create a centripetal force. Right? So the net result of gravity and the normal force is going to create a centripetal force. Meaning here, if I write down the net force, this time I'm going to add together the normal force and gravity added together. They're both going in the same direction, and that's going to be equal to my centripetal force. So once again, let's do an example just with some numbers here, and we can figure this out. This time I'm curious, what's the normal force going to be on you when you're upside down on the roller coaster? So that's my ultimate goal here. Let's just make up some numbers here. So the mass, once again, it's going to be you, 50 kilogram mass. That's a pretty light person. That's like 110 pounds. So maybe that's more like a child or something, or an older child. And since this is a roller coaster, it's going to be pretty big. So how far is this radius in this roller coaster from the top to the middle? Let's call it 20 meters or something like that. It'd be a pretty big loop on a roller coaster. And let's say you're going reasonably fast here, maybe something like 50 meters per second, right? So that's like 100 miles an hour. So it's a really fast roller coaster. And let's see what this is going to feel like. So once again, I'm curious. The question I'm asking is, what is the normal force? What's it going to feel like for you in the roller coaster? Remember, once again, if you're just on flat ground, whatever the normal force is kind of your clue to like how much you weigh. Oh yeah, here, let me remind you. When we went into the elevator and we were standing on the scale in the elevator, so there's you on the scale in the elevator. Let's say that we had some acceleration in the upward direction. When you had acceleration in the upward direction, you had to have a bigger normal force. So Fn increases when you're on the scale, and that's going to make you feel heavy. So remember, when you're in the elevator and you are at the bottom floor and you push the button to go up and the elevator starts to go up, you're accelerating up, the normal force increases, and that we saw that on the scale, and you're going to feel heavy. So whatever your normal force is going to relate to your weight right here. So I'm curious in this roller coaster situation, what's the normal force? And that's going to kind of be how much you feel like you're going to weigh. So let's just plug in numbers right here. So up here, I'm going to just take this and write it down here, but I'm going to write the normal force is going to be whatever my centripetal force is minus the force of gravity, right? Because when I pull this over to that side, it's going to be minus. Okay, so normal force, the centripetal force, once again, is m times v squared over r. And then the force of gravity, oops, why do I keep writing equals there? Minus mass times gravity. Okay, so then we're just going to plug in the numbers here. Mass, once again, I'm going to drop my units. 50, oh, there goes the lights in the classroom. Let me get the lights back on. Okay, so let's see, 50 is the mass. The speed is also 50, which is pretty big. Going to square that. Going to divide it by the radius, which is 20. And then, oops, why do I keep writing equals? Minus mass times gravity. So that's 50 times 10 again. Actually didn't do this one out in advance, so we'll just do it live on screen here. Clear that away. So we get 50 times 50 times 50. That's 50 times 50 squared. And we're going to divide that by 20. So this is 6250 over here. And then we're going to subtract out 500 minus 500. So this whole thing is going to be 5750. Okay, so what does that really mean? 557.50 newtons. This is how much you feel like you're going to weigh in this situation. So if you're going on this roller coaster and it was really going at 100 miles an hour, which is pretty fast when you're upside down and it's this 20-meter radius roller coaster, you're going to feel like you weigh 5,750 pounds. Well, how does that relate to what you usually feel like? Well, on flat ground, once again, here we'll just go back up here. On flat ground up here, your normal force is equal to gravity, and that was 500 newtons. So on flat ground, you feel like you weigh 500 newtons. Upside down in this roller coaster, you're going to feel like you weigh 5,750 newtons. So that's going to feel like a lot. That's like 10 Gs basically when you're upside down like that. So this roller coaster is, maybe you don't want to be going at 100 miles an hour upside down in this roller coaster. You'll feel comfortable. You'll be stuck to your seat, right? Remember, whatever this normal force is what you're going to feel like is this centrifugal force coming out, right? So you're going to feel really, really heavy, but you're going to be upside down in the roller coaster when you're feeling really heavy. Yeah. So that's just a couple of examples. We're going to talk a little bit more about what if you're going slower and what if you don't have enough speed and things like that when you're upside down. So hopefully this was interesting for you all, and we'll talk some more in class.